All right, so whenever we form salts or ionic compounds, they're very stable. And since they're very stable, just like a ball rolling down a hill becomes more stable, it releases energy. Forming these salts will also release energy. We call that exothermic. And that just means that it releases energy. And so we can think about what happens when we take, for example, solid sodium, combine it with chlorine gas, and form sodium chloride, right? We know that the overall process is exothermic, but what about all the steps in between? And what about thinking about how much lattice energy is released or formed? So that's what the Bourne-Haber cycle is. So the Bourne-Haber cycle is a hypothetical. So it's not actually what happens, it's just hypothetical. Series of steps that represent the formation of an ionic compound. And what this allows us to do, it allows us to calculate the lattice energy. And the lattice energy is related to the ionic strength of these compounds. And so if we calculate the lattice energy for a bunch of different salts, we can figure out, okay, which one of these salts are more stable or less stable, that sort of thing. So for example, if we have cesium solid combining with half an F2, we'll learn later on that all of our halogens are always diatomic elements. So it's always like F2, Cl2, Br2, that kind of thing. And they'll combine to form one cesium fluoride as a solid. The noble gas or the halogens are also always gases. If we think about the overall energy change in this process, we get negative 553.5 kilojoules per mole. We'll learn about kilojoules and whatnot in delta H later on. The main thing that we want to know is that this number is negative, which means that we release energy. And we become more stable, right? So we release energy during this reaction. And so this delta H of F, that means formation, right? What it is, it's a sum of all the steps, right? It's the overall energy that is released throughout this whole process. But throughout this whole process, there are multiple steps that they can undergo. So what we can do is we can break apart this process into steps, and then we can add them up. And all of our steps have to add up to be equal to this overall number. Energy cannot be created or destroyed. It can only be transferred. And then we can solve for an unknown. Generally, that unknown is the lattice energy, but it could be other things if you already know the lattice energy. So let's think about this process here and what steps we have to undergo. First thing we see is that the cesium is a solid. All of our chemical reactions are going to occur during a gas phase. So the first thing that we're going to do is we're going to turn the metal into a gas. This is what's known as sublimation. Sublimation is a phase change from a solid straight to a gas. So what's going on here is we have solid cesium going into gaseous cesium. And we can calculate that energy, or we can experimentally find that energy through other means. And in this case, it's 76.5 kilojoules per mole. Again, don't worry about the units here. We'll learn about that later. Another thing with these halogens, they are always diatomic. So it's always, F2, Br2, Cl2, whatever. But here we only have one F. So what we need to do is we need to break that bond. So we need to break F2 into just F, right? So we're going to break that chemical bond. So we're going to go from half an F2 as a gas to just one F. And that's something called bond enthalpy, which we'll learn about a little bit later when we get to covalent compounds. In this case, it is 79.4 kilojoules per mole. Notice that both of these numbers so far have been positive numbers. That means that we have to put energy into the system for this to work, right? We have to roll that ball up the hill instead. All right, another thing we have to notice is that in this solid cesium, we have no charge in the cesium, but over here, we've got a +1 charge. So what we have to do is we have to ionize the metal. And we know that value already. That's our ionization energies. So for example, cesium as a gas to go into cesium plus that removed electron. This is also a positive value. So even though we say that cesium wants to lose an electron, it doesn't actually want to lose an electron. It's just that it's relatively easy to remove that electron. So for example, this value is 375 kilojoules per mole. If we try to remove an electron from like fluorine or something, it would be way bigger. All right, another thing we notice is this fluorine over here, when it's in its diatomic form, it does not have a charge. But over here, when it's in the cesium fluoride, it has a -1 charge. So what we have to do is we have to give it the electron. All right, so we're going to give the nonmetal its electron. And that's our electron affinity, right? We looked at that in the periodic trends. So we're going to go from F to F minus. Now, this part is exothermic. This fluorine does want this electron, so we'll get a negative number, right? We're going downhill here. And then the final thing that these ions are going to do is they're going to form our lattices, right? So they're going to go from basically being apart to form these big lattices so that they can bond to multiple other ions. Right, so we're going to say that we're going to allow ions to form a lattice. And since positive and negative charges like each other, when you allow them to come to contact, that releases energy, right? So that's what we're going to call our lattice energy. So here we're going from cesium as a gas with its positive charge to fluorine as a gas with its negative charge to solid cesium fluoride. And this delta H is our question mark, right? We're not quite sure about that, what this is, right? That's the whole point of this Bourne-Haber cycle, is to figure out what this lattice energy is. All the other steps, we can calculate these values or find them experimentally through other means. The lattice energy is much more difficult to do. And then the last value we know is the sum of all the steps, right? We can do this reaction and we can measure how much energy it releases. And so what we know is that it releases negative 553.5 kilojoules per mole. And we also know that that number is the sum of all of these steps, right? So all steps must sum to equal our overall delta H, or delta H of formation. And so what we do is we just take these numbers, we plug them into our equation, and then we solve for our unknown. So the first step was 76.5 kilojoules, the second was 79.4, the next one is 375.7, the next one is a negative number, 328.2, right? That's giving that fluorine that electron. And then we have our X value, our lattice energy. We don't know what that is, but we do know that all of these steps add up will be negative 553.5 kilojoules per mole. And so then what we can do is we can rearrange that equation. I'll leave that up to you to do. X here will then equal negative 756. Negative 756.9 kilojoules per mole. And that's what's equal to our lattice energy. That's how much stabilization this interaction between these positive and negative ions releases. Again, note that it's a negative number, so this is causing the system to become more stable, same like we're rolling the ball down the hill. And so the end conclusion of the Bourne-Haber cycle is that the formation of a salt isn't exothermic / favorable because a nonmetal wants an electron and the metal wants to give up an electron. Right? That's not why salts form. That's not why they're favorable. That's not why they're exothermic. It's not because these ions want to gain or lose an electron. It is because of the positive and negative interactions that form in this lattice. So it is because the positive / negative attraction in the lattice is highly stabilizing. And here's the same process in just a diagram form. So here's our Bourne-Haber cycle for sodium chloride. These over here are the kind of individual steps that we talked about. So notice how a lot of these take energy, right? We're going uphill. There's those. The only really downhill step is giving that fluorine, or in this case, the chlorine, its electron, right? So that part is, downhill. And then this right here is our overall. So we can see overall, we are indeed becoming more stable. We're going towards a lower energy state. But the reason that we're going towards that lower energy state is due to this lattice energy, right? This favorable interaction between the positive and negative ions. So the lattice energy is the major driver of salt formation.